Make sure I get my announcements. I'm sure.
We're going to do announcements after.
Okay.
You know, it's actually music. It goes to the web.
What was I going to do with this other than drink it?
I'm there, but I see just myself and the presenter.
5 seconds!
So what shall I do?
Where's the fanfare?
I say that.
I wanted to hear the fanfare. All right. Those of you, listen up, sit down. So there we were.
Yeah.
Schrodinger was driving down the road.
Okay.
He was driving down the road, got pulled over by the highway patrol. Highway patrol says, going too slow.
We are.
What's in the trunk? And Schrodinger says, well, it's my cat. And the highway patrolman said, well, I have to take a look. Something sounds strange there. Schrodinger opens the trunk. Highway patrolman looks in the trunk, says, your cat's dead. Schrodinger says, well, yeah, now. I'd like to thank Professor Nash for that. No, it's I've seen it before. Heisenberg was driving down the road. The highway patrol pulls him off. Heisenberg was driving down the road. Do you know how fast you were going? No, but I know exactly where I am. What does it all mean? I'm uncertain. Okay, coming attractions. Harbold from this morning. Technology problems, didn't work, c'est la vie. Then after that, we're going to have a short PowerPoint slideshow from Dr. Ting, who sent this in his absence. He couldn't make it today. And finally, after that, we're going to do rumors, announcements, gossip. Embedded Systems Conference guy, Peter, and whoever else wants to promo something, sell something, invite participation in something, that will be your chance to speak. And then after that, the green erase portion. And then after that, the fireside chat. Okay, you're on. Tell us who you are before you start.
Okay, how do I switch it on? Is it on or? It's on, good. My name, am I going to be on camera? Thank you. Ready? Okay, sit down. Okay, my name is John Harbold. My talk is on C macros for the Arduino 4th. And I did this talk 3 years ago, but now I've done, expanded on it just slightly. I'm going to present ANSI C macros that can be used to create an annotated 4th dictionary running eForth on the Arduino. The Arduino development system is based on the GNU compiler collection, GCC. Ting's eForth is written in, for the Arduino, is written in C. The problem is his dictionary, let me see if I can, looks like this. It's just a bunch of 16-bit hexadecimal numbers, which don't really convey a lot of stuff what's in the dictionary. Okay, the C language has a programming facility called macros. These macros are expanded before the C proper compiler is executed. And this facility can be used to create various fields, namely the length, name, code, and parameter fields of a 4th word. Okay, there's Ting's. This works, but it doesn't really convey a lot of stuff. And here are the descriptions of the E4th words. There's a length field, which is used for searching for words. There's a name field, which is used to give the fourth word its name. There's a code field, which will execute the parameter fields, and the parameter fields will be the things that the code field will execute. Okay, the link field, I have 2 words for it. The link field will write the pointer where the last word is, and then when you complete a word, then the link pointer will get updated. The name field is a counted string, and the first byte is the length, it's a byte, and the rest are the bytes of the name. For the Arduino architecture, a 16-bit word has to be aligned on an even address. If the name field happens to be odd, then it gets padded with a null character. And here are the names of the name field macros. There's and that will generate a counted string from that. The fourth word takes and will have put a link field prior to the name field. Then there's a colon word, which does the above, and it adds for the code primitive, it just adds the do list. And the code fields are just basically that. You put the name of the fourth word that you want to be executed in this location. And the parameter fields, I have 4 of them. There's a primitive. In Ting's eForth, there are numbers that are related to primitive activities. We'll show you later. And then there's a thing where if you would just want to put a word value in the fourth word. We also have utilities, these C macros. There's begin until, which will create jumps for you. There's begin again, which gives you an infinite loop. There's if then, obvious. Then there's also if then else. There's begin while repeat, which gives you a finite loop base. And there's for and next. There's something called af then, which is used in a for and next. That's just what I noticed what was in his code. Okay, the first word in Ting's thing is something called temp. And what this does is that's the fourth word will generate a name TMP. It's an inline, and the primitive there is next. And then for some reason it's got a 100 hex, and then end word. Now, this is what the macros will generate, is this. As you can see, this is the link field. The reason I did it this way, it also puts C comments, which annotate what you're writing out there. Next one is the name field, okay? And you can see, here's the counted string. There's 3 characters, and it's TMP. The code field 6, that's means something I don't offhand remember. Then it gets padded. Oh, these numbers here, these are addresses. Okay, and the primitive here is a 4, and then here this is a pad showing it's a 0, and there's more. We have a number, a 16 hex, also with a pad. And here I'm trying to figure out, this is the word field that we had before. Here is a colon definition, rotate. And rotate, the next thing it does is it puts the top of the stack to the R stack, does a swap, returns what was on the stack, and then does a swap, and then exit in the end of the word. And this is what that looks like. This is the link field. This is the name field right here. This is the code field, primitive 6, which I believe is do colon, padding. Here is the code word for do CFA. Here's the next one, which is swap CFA. Then there's, oh, I'm sorry, back up. More, meaning this is 2R. This is 2R, this is swap, and this is the CFA of these words. Mind you, it's been 3 years since I've done this. And then here, this is popping from the R stack, then it does a swap, and then exits. Here's another one, ABS, absolute. You have a dupe, a check if it's 0 or less than, and this also shows now the if and the then. And if this thing is not 0, then it will do a negate. No, if this thing is negative, it will do a negate, then exit. And the code here looks like, looks exactly like that. You can see there's the name field. Here's the code field right here. Again, number 6. There's a pad in there. Here's the dupe, 0 less. And then here's where if, now mind you, this is important, this address needs to be saved. And you can see here's the thing, if this were true, you do a Q branch CFA. And here you can see if you come down here to this point, you branch to 06AE, which will be, wait a minute, 06AE, god damn it. Oh, that branch is around. This branch is around. Right, okay, I'm sorry. This branches to here. And then this is the terminating exit. This is showing what the, oh, that was the thing. You notice that I have things like this, C, dot C, dot C, dot S. That's what these guys are. Okay. And then this is the definition for, temp CFA. Then for rote, and that's it. I just want to have a real quick thing. So, questions? Anyone want to? Because I meant to give this to Ting, but that's when he said, I don't want to do eForth anymore. So, oh, I'm sorry. Let me show you what the actual code looks like. Come on, don't pull this nut act on me. Okay, as you can see, here's the first word, right? Then we have hold, span. Okay, these are a bunch of primitive words to have here. So I can get down to something a little more complex. Okay, here's like equals. You can see here, you do an XOR, and if it's not 0, then you do a literal, which will say this will put a 0 on the stack, and you'll exit. Or if it's not, then it'll do all F's and then exit. Okay, here's a more complex. This is um/mod. And you can see there's an if with a or next in it. with another if. Here's an if then else, and then that's your loop, and then when you're done, this. Now, let me show you what the resulting code looks like. Here's the resulting expanded C macros. So you can see they're a little complex, but at least there are comments in there to tell you what. So you can see here, for the HLD, the link field here points back to the previous word. And the same here with span. Span comes back to here. Okay. And you can see as we get further down to the more complex, well, then these things get larger and larger and larger. But this will generate the array that Ting had. So now, do you have any questions? This is ANSI standard C, and it does generate the code. Yeah, Charlie. This is just getting the dictionary. Well, no, what it does is, remember okay, you don't, no, that's okay. No, it's not a dumb question, no. This is what Ting's dictionary looks like. Okay. And anybody want to decode this? Right? Well, there are just, yeah, there's actually just went to 32-bit now, 16-bit. I don't know, 32-bit. So, anybody want to tell me what all this means? Yeah. Yes, exactly. This will generate my program will generate a C file, which you can then substitute for this guy right here. In fact, here's what I basically did right here. Sure.
Do you get this into your Arduino, the usual Arduino bootloader, or is it?
No, you just put it into the E4th code, which when it gets built, we'll link this code in with the rest of the.
Right, but it gets your E4.
Oh, I don't know.
Oh, okay.
I don't know. That's all I did.
Okay.
All right. So that's basically it. I know that it kind of needs to be in a more, I could do indenting and all that kind of stuff to make it a little more readable. But the nice thing about it is it does have C comments in there to tell you what the address is and what the value is. Like for HLD, you say, well, what's the primitive? Well, the primitive is at 410. That's its value. Same thing with the NFA. It's at 040C, and you have 4 characters, a 3, an H, an L, and a D. And like here, this primitive is at 410 and 04, which I think I can look that up because that's something that Ting did. Yeah, these are the numbers right here. So you can see that 4, the primitive 4 is a do constant. All right, so that's the way I did it, which means what's nice about it is if you want to go in and modify how the E4th dictionary is, And well, you can just write your own instead of having to figure out what all this nonsense is. See, names convey information, numbers do not.
Unplug
And get the hell out of here? Yeah.
No, you have time for a couple questions.
Okay, anything else? Move, right? I'll move.
Yeah.
Yes. Okay, anything else? Anyone here doing E4th using Ting stuff? For the Arduino? Well, okay. You know, well, yes, go ahead.
Wouldn't we just need to use similar macros instead of C?
Well, the reason being is Ting's E4th is written in C. So I just said, okay, why not?
Version of it.
Yeah, why not just do it? You can do it. In fact, what inspired me was PDP-11 4th was using assembler macros, and that's what inspired me. So
One of the goals in writing a 4th in C for the Arduino is that it opens the possibility that you could write something that can be conveyed to the Arduino through the Arduino's loader rather than reprogramming the flash from scratch with a USB programmer dongle.
Right, exactly. Take from me.
All right.
Can't see it.
Thank you, John. All right. Then we have the... All right. That's a relief. So I wanted to take this opportunity to indulge in a couple of thank yous. I'd like to thank Dennis for all his tireless efforts with the web stream, and I'd like to thank Sam for that also. If you listen very carefully, you can hear in the distance, you can hear the internet applauding. So I'd like to thank Dave for the use of the hall, and I'd like to thank Stanford as well. I'd also like to thank Dave for ordering lunch. Yay, lunch! And all the 3 dozen other things he's done for us, including putting up with me. So, Dr. Ting couldn't be here today, but in true Ting style, he, at the last minute, prepared this. He had a video that he was working on, but he couldn't quite get that together in time. So just imagine one of Ting's demos. You've probably seen half a dozen at least. The idea here is that this is a PowerPoint slideshow with sound. Everybody remember Clippy?
This is CHK. I'm sorry I cannot be at the meeting today, but I would like to share with you some work I'm doing for the last several months. And I'm trying to write a book for Launchpad 4. And the title is will be Zen for 430 Launchpad. Okay, this is a Launchpad for very nice little board from Texas Instruments. So, in this talk, in this presentation, I would talk about the thread models and compare them. And I would concentrate mostly on the 430E4 version 4.3. And I talk a bit about the 430E4 IDE, which is a very nice terminal emulator for E4. And for demonstration, I have a nice Morse code beacon demo. Okay, I tried 3 different techniques in these 3 different models. The next macro in the indirect thread model has 2 instructions, and indirect thread model has only 1 instruction. And subroutine thread, it is just a plain return. For high-level colon commands, the indirect thread model has a do colon routine, which has 4 instructions. And the direct thread model has a call do list instruction, and call do list subroutine has 4 instructions. And to exit or nest the high-level compound commands, the indirect thread model has 3 instructions, and the exit in direct thread model has 2 instructions. And in subroutine thread model, it's just another return. The token list in the indirect thread model and the direct thread model has execution address as tokens, so they are address lists. And in subroutine thread model, it's just a sequence of call instructions. So here is a pictorial presentation of the different fields of commands in these 3 models. From the left is the indirect thread model. It has 4 fields: link field, name field, code field, and a parameter field. In the direct thread model, there's only 1 code field. There's no parameter field. And in the subroutine thread model, the code field has just plain machine code. And so in the indirect thread model, the code field of primitive command has just a pointer which points to the parameter field next to it, which contains all machine code. And in the parameter field of the compound command, it is a token list of addresses. In the direct thread model, the code field has machine code, pure machine code, and that's field. And in the compound command, the first instruction is a call do list command. And then the address list follows this command. In the subroutine thread model, the compound command just have a sequence of subroutine call instructions. And in the primitive command, just have other machine instructions. So these are the different model, how different model looks inside the dictionary. Here I'm comparing the overheads for the primitive commands and compound commands. The indirect thread model, the overhead for a primitive is 6 bytes and 4 cycles. And the overhead for primitives in the direct thread model is 4 bytes in space and 2 cycles in time. In the subroutine thread model, for a primitive command, the overhead is 6 bytes and 8 cycles. The overhead for colon words or compound words in the indirect thread mode, it is 8 bytes and 12 cycles. In direct thread model, 8 cycles, but 17 cycles. And in subroutine thread model, 6 bytes and 8 cycles. Overall, the code object code size, the direct thread model has the smallest, but not by much against the indirect thread model. 4,182 bytes for direct thread mode, 4,228 bytes for indirect thread mode. And subroutine thread model is bigger because subroutine calls are 4 bytes for each call, and the size becomes 4,938 bytes. Source code are pretty much the same, although the direct thread model is the smallest. To run 10 million empty loops, the indirect thread model took 16 seconds. The direct thread model took 12 seconds, and the subroutine thread model took 18 seconds. This is not quite fair because this essentially only tests a jump instruction in the loop. So a more realistic test is to search at string 1, 2, 3, 4, 5. And this traverses the entire dictionary and then do a number conversion. So to do 10K of searches, it took 23 seconds in indirect thread model, and 19 seconds in direct thread model, and 24 seconds in subroutine thread model. So overall, direct thread model is the shortest, fastest, and cleanest. And that's the model I used to write my book. The reason is the single instruction next. It pushes it over the other 2 implementations. And it's the very nice. This is very nice instruction in the NSP 430 because it has a auto increment memory fetch mode. It also affirms the direct fed model in the original eForce model. This is very nice that I can get back to the original eForce. So here is what's in the 430 eForce version 4.3 in direct thread model. I retain 182 commands out of the 224 from the original eForce model. To simplify the appearance of eForce, I took out the name fields of 50 commands. And so only 132 commands are visible to the user. For performance, I coded 83 primitive commands versus 31 in the original eForce model. So only there's 99 compound commands left in the system. Okay, here is the 430 eForce IDE, and this is a gift from Dirk Rule of foreforce.org, and it released a nice force system called the 4eForce, and with the IDE. And this integrative developed environment contains a flash downloader to download object code to Launchpad. It has a very nice terminal emulator. You can interact with the force system. And it supports text file downloading. It has a text editor. And it also supports a turnkey system generation. So here, this is the how 430 eForce IDE appears. It's a very nice window with all the nice buttons and fields showing you everything that you want to know about the system and to exercise it. Okay. The prior version of 430 eForce can be downloaded from this link. It was still in the subroutine thread mode, but not much different from the user's point of view. This is the only thing you need to get eForce running on Launchpad, and that's what I call the Zen of 430 Launchpad. So here are many experiments you can do right off with the eForce on the Launchpad. You can turn the LED on and off because the output port is 21, and you store 41 into 21. You turn both LED on, you store 0 in 21, and turn both LEDs off. Put a 1 in 21, turn the red LED on, and put a 40 into 21, turn the green LED on. So that's very nice. And the better demo is to generate sound. If you connect an 8 ohm speaker to pin 2.0 and ground and type these numbers into the various registers, then you can actually produce a nice tone. Now, this is the easiest way to generate sound Launchpad. It just can't be any simpler. So based on the tone generator, I use Doug Brewer's then code to build Morse code beacon. It uses a timer A1 to produce the tones. And when the short bits are running, it lights up red LED. If the dots are running, it lit up the green LED. So here it goes. I hope the video demo will show you all this very interesting experiment. Well, I don't hear any questions. So, thank you very much. Have a great 4th day. Bye-bye.
All right, those slides will be up in the meeting notes in some form. So if you missed the link, that will be made available. I'll try to remember to send that link out to the email list as well. The next thing on the docket is Peter, wake up. Is rumors, announcement, gossip, slander, libel. If you know the difference between slander and libel, you can explain it after the meeting is over.
Hi, I just have a few quick job announcements. I have a few quick job announcements. My name's Peter Milford. I'm CTO at a funded startup called iFluence. We're transforming intent into action through your eyes. And we're developing a variety of eye interaction technologies for upcoming wearable display systems, like an augmented reality headset, for example. We're looking for an Android engineer who's good at doing demo applications and developing user experience, user interfaces, and is quick at prototyping, and hopefully also understands the access to lower level functions through an NDK. We're also looking for a software engineer who's excellent at embedded C programming and probably has a Linux background and hopefully can contribute at least a little bit in the Java Android world. And we're also looking for a computer vision expert who can help us develop our eye tracking algorithms further, and also a director of software engineering to help us manage the people we're about to hire. So please, if you know anyone who might be interested or anyone here who's interested, please come and see me at a break. And the company name is iFluence Inc., and 3 of those jobs are posted on the website. And also, we'd like some interns, young and enthusiastic in any of those areas. We're in the Bay Area. Thank you. Who's next?
I'm sorry, I don't know your name, but one of you gentlemen was talking to me about the possibility of doing a paper for the Embedded Systems Conference. That wasn't you, but okay, you'll do. It's a different guy.
All right, then for the record, my name is Randy Liebernight. I was talking to you about wanting to recruit people to do papers for the Embedded System Conference. If you had someone who wanted to do a paper...
There was another guy that was talking to me about that, Randy.
Cool, then send him to me.
If I remember who he was, sure.
All right, or put my email address on the board here.
Yeah.
So Embedded Systems Conference in Boston is coming up in May. You're probably not going to Boston, but if you are, let me know. The thing is, the request for papers is due in 2 weeks for the Boston conference. They seem to want these proposals for papers like 5 months in advance. So I'd love to see the ideas here presented at the Embedded Systems Conference, and since I'm on the program committee, I'm trying to recruit more people to do cool things like what I hear about here. Because they only give you a month's notice, I want to give you 6 months notice. The Santa Clara one will be in July. But if you're interested in doing a presentation, they have like 200 people do presentations at this conference over the course of 3 days. If you're interested in submitting a proposal to do a presentation, I can send you the invitation for the Boston conference. You have plenty of time to make a proposal before they give you 1 month to turn one in instead. So my email address is rliebernight@gmail.com. I'll write it on the board. I have to leave a little early today, so I won't be around to chat later. And I think it'd be cool to get our ideas out to a wider audience. So that's what I have to say. Who's next?
Yes, Charlie, you want to make your way to the front of the room here? I want that. You get to keep your tablet. 2 tablets and call me in the morning. There once was a young fencer named Fisk, whose fencing was exceedingly brisk. Was his action, the Fitzgerald contraction, reduced his rapier to a disc. There'll be a short lull in the action. Yes.
Huh? Right here?
Hello, my name is Jason, and
Get the mic first.
I need the mic.
Or else the rest of the world.
All right. My name is Jason Damish, and I'm getting through Petzold, learning some APIs, and one of them is the Windows API. And I've been doing this in SwiftForth. I really like SwiftForth. I think it's a good language, and but I wanted to take a look at some other Windows Forths to just kind of see if maybe I would want to switch at some point or not. But what I really want is a nice, smooth interface to the Windows API. SwiftForth has, basically you just kind of like name the function you want to grab from the DLL, and then put the parameters in the order that they appear in the C documentation, and you don't have to convert the pointers. And if anybody is aware of a Windows Forth that has this, I would be interested in finding more about that. That's basically my question, and I thought maybe this would be a place to ask that question.
Okay, let's see. Yeah. Ready for me? Want me to come over here? Oh, I can see myself here. All right. Okay. My name's Charlie Shattuck. I do the customer support at Green Arrays Incorporated, which is why I'm in charge of this today. It's going to be a little bit loose. I've got a list of people that may or may not speak here. Actually, I think they all may. Greg is going to give a talk via video about what's been happening the last year or so. Huh?
No, he's not gonna. It's on my computer. We're gonna play a file. Yeah, he may get back in time to talk to us in person. Yeah, remotely. I'm gonna have some things to fill in with basic building blocks if it turns out we don't fill up the time. I may not. If I'm lucky, I may not talk at all. And if you're lucky, maybe I won't talk. We'll see. Daniel Colney is an associate in the Czech Republic, and he did an app note for us called the Incremental PID Controller for a Brush DC motor. It's a beautiful app note. He's put together a video that we're going to watch as well. And I believe he will be available for real-time question and answer, but I foolishly didn't leave myself any way to communicate with him today. I usually talk to him via, yeah, Dennis says, yeah. Daniel, I apologize. I didn't bring Skype. I didn't bring your email address. I didn't know how to get in touch with you, but fortunately, Dennis did. Franklin Amador is going to talk about, he's another associate who did an app note using the Green Arrays development system. He's going to talk to us about exploring one-wire devices. That's Dallas one-wire devices, right? And then we may get to have Greg Bailey's Q&A about his app note 007 about the software-defined NIC. Which reminds me, I have 4 copies of that app note for anybody that can't get to it for some reason on the internet. And if anybody would like to look at these, you're welcome, but there's a string attached. If you take one of these, you better ask a question, an intelligent question about it, okay? So what, can I leave them right here, Brad? And if anybody wants that, you know, just find some way of getting one and think of a good question to ask. So I think what we're going to do now is we're going to play Greg's video, which is an introduction to green arrays and what we've been doing for the past year. Sound okay? Let's see how that works. Oh, dang. I'm going to... Where is my mouse? You can't hear it, right? That's because this wire needs to be plugged in. Pardon? Okay. Oh, good. Okay. Let's start this over.
I'm Greg Bailey, and I am here to
Okay.
summarize the green arrays for the past year.
Put the mic up.
This project for an unidentified customer and unidentified purpose. This ended up consuming the time of Chuck, Mark Smader, and me from about September of last year through February. And it consumed Mark and me for several more months until about July of this past summer. It was an interesting project. It never led to silicon for interesting reasons. The main reason being that the market in which we were engaged was that of Bitcoin mining equipment. That is a market with a giant built-in arms race and a moving target, inevitably moving target. People are doing 14 nanometer FinFETs now to make silicon for Bitcoin mining. The problem with that market, of course, is that the aggregate difficulty level of the network doubles basically monthly. And that means that the amount of money that you could potentially earn with a piece of mining hardware is diminished by a factor of 2, basically monthly. So 10 months, 1024. If you were making $1,000 a day with your mining equipment downstairs, and 10 months later looked at what was happening, you'd be making maybe $1. And that certainly wouldn't pay for the power to keep the thing running. And that was the problem. We started out with what was going to be a design exercise at 180 nanometers to calibrate our methods. That turned into 65, that turned into 28. The path that it led us was interesting, and it taught us a lot about ourselves and our capabilities. Perhaps the most interesting thing that we learned was that building, or at least laying out silicon at 28 nanometers with homebrew CAD system is not infeasible. After we had basically ceased work on the 180 nanometer effort of that project at the end of February last year, we did several interesting things. The first thing that we did was to redesign and rewrite our EDA tools. OCAD had two problems. One of the problems that it had was that there's a man in San Jose that thinks he owns it. And whether or not he actually has a claim to owning it, he's well known to be able to litigate endlessly over his thoughts about things. And so we're better off doing our own thing, doing something completely independent. It has nothing to do with any work that Chuck was doing between 1999 and 2009. The second thing is that we were able to considerably simplify the design tools by moving them to a polyforth environment on the x86s. And that's what we've done. It runs faster, it's an easier to use human interface, it's easier on the eyes to look at, and the code is simpler. Plus, it's more mutable. We factored it in such a way that the design tools themselves are independent of the definition of the process being used. And so you can take a design basically and run it on the same tool set as a design for an entirely different geometry. When you fix the problem in the tool set or make an enhancement, it's already there in the next technology. So we used this new system, which we call GLOW for the moment, to produce layouts at 28 nanometers, GlobalFoundries 28 nanometer process, which has entirely different and bizarre design rules, and it calls for an entirely different layout scheme. The tiles are not square if you're going to use tiles, and we do. The whole method that we used to use for making contacts doesn't work. The whole method we used for routing doesn't work because, among other things, the design rules forbid you basically from making free use of polysilicon as a signal carrying wire. So we had to completely change a lot of things. And we had to also adopt a layout strategy that is basically demanded by the design rules themselves. And so our layouts there look nothing like our layouts in 180 nanometers. But the interesting part was that with a small finite amount of effort by Mark and me, we were able to make a CAD system that could lay out silicon at 28 nanometers, and that layout could pass the design rule checks and the manufacturability checks from the manufacturer. We thought that was a good thing to know. It means, among other things, that a lot of the urban legends that we hear about how it's much more difficult to design at the advanced geometries, well, they're BS. There is not that much different about it to require an entirely new set of skills. Electrically, the simulators don't tell us that there are big differences. So where do the urban legends come from? Well, you know, a lot of times urban legends are started by somebody who heard something from somebody in a bar and has never actually done it themselves. And there you go. We have done it. It is not that hard. And we're confident that if anyone comes up with money and wants us to design something in advanced geometry, we can do it. So that was the excitement of that, of basically all the time from our last fourth day until midsummer this year. Now, Chuck has been working on some stuff since last February, and he'll be talking about that in his fireside chat. But mainly, this is what we've been up to. We have also engaged with a couple of potential interesting customers who had really nice sounding product ideas. And something may very well come of that. We also have someone who is demonstrating what can be done in real-time processing of video by chips like ours. And he's showing this to the Army, and the Army may end up doing several interesting projects after the first of the year involving the GA-144, which we're looking forward to greatly. And finally, one other thing that we did last year, there are people who have expressed a desire to program our chips in C. I understand why. There's a whole theory in middle management in the United States of America, at least, the gist of this argument, the gist of this fantasy, is that learning a programming language is hard. That you have to go to graduate school to learn a programming language, or you have to spend months to learn a programming language. We all know that that's BS. What we all know here in this room anyway is that learning a programming language is easy and takes a matter of hours or days at most. What we also know here in this room is that learning an elaborate library can take a very long time indeed, particularly if the library itself, such as the Unix library, is not all that well documented. Now, when I look at the number of shelf feet that my Unix documentation, my Unix programmer's documentation took, and I look at the number of shelf feet that my Windows programmer's manual takes, I understand that the issue is not the programming language, but the libraries, right, and the APIs, which is all about an operating system, and it's all about other things than the language. So, we know it's a fantasy. We know we know that it is an absurd notion, and yet it is widely believed in business in the United States that if somebody doesn't already know a programming language, you may as well not think about having them be productive for months because it's going to have to go learn it. That is a problem. That perception, that mistaken idea is a problem. And so one of the things that we can do to counter it is to address it. Well, there's no way that a person is going to reasonably program a node, an F-18 computer, in C, or in Fortran, or in COBOL, or in RPG, or in any other high-level language, Perl, you name it. It's not going to be programmed in any of those high-level languages because, frankly, an F-18 computer does not have the resources to run an existing program written for any high-level language, and that would include a Hello World in most of the languages, because Hello World involves a library call usually, doesn't it? Now, here we sit in a little bitty computer, the F-18, which has too few resources to even run a classical fourth system, and therefore to run an existing fourth application. So we know that it is silly to talk about programming nodes in C, just as silly as it is to talk about programming them in fourth, as we all understand fourth to be. What we can do, however, is build virtual machines, and we have built a virtual machine very successfully that runs just fine to run polyfourth on these computers. We also have another virtual machine that was done by John Reibel and Bill Munch to run eForth on it. And so this is a nice demonstration of the fact that you can give yourself access to all the capabilities of a high-level language and all of the things that you can do in high-level languages, such as programming protocols like TCP/IP or perhaps the Bluetooth stack, and do very nice work with it. So Charlie has been working along this year toward putting a C virtual machine on the chip. Will it be efficient? No. It will be less efficient probably for equivalent work than polyfourth, simply because C requires more memory cycles than fourth does. C requires a more rich instruction set than fourth does in order to be efficient. That's just the way it is. Nevertheless, to run high-level protocols or to do supervisory work does not necessarily require the speed and the intimate performance of an F-18. So any virtual machine that is able to run all of this complex stuff is fine. And if people don't want to take the necessary few days to learn fourth, then they're welcome to find another way to program it. And that's been our position all along. Well, what we are going to do is to carry on what Charlie has been doing, and we'll get to that later, but it's a bit arrogant of us to say, well, if you want to program in C, you just have to make your own virtual machine. We haven't taught people how to make virtual machines, and that's not an application skill that most people have. Most people haven't ever thought about designing a computer and implementing it in software, and so perhaps it's a good idea to actually show someone how to do it. So we will have a viable C programming environment that at least allows a person to take his existing methods from C and use them on our chip. That's the way it will be. But that's the most interesting software development from last year, because, other than Glow, because we were busily engaged for most of that time trying to design this chip and meet a moving target, which we could not do. What will we be doing next year? The next year is going to have efforts in hardware and in software and hopefully in company development As far as the company development is concerned, we're going to continue to look for customers. We are seriously thinking of making a nonprofit whose charter will be to educate kids in the methods of programming that we use, the methods of hardware design that we use, and the reasons for doing these things. We should be able to put together a fairly interesting supplementary course. And so we may find out what we can do in the context of a nonprofit with independent funding to offer such courses to youngsters. Specifically, I'm thinking brilliant high school students. A brilliant high school student does not need to know anything that he shouldn't have already learned by now in order to both program and to lay out CMOS silicon, other than how to use the tools. So it'll be interesting to see if that goes anywhere. We will try. We will try if we're committed. The software efforts that we're going to be engaged in next year are focused on things that we would have done last year had we not been engaged in that layout project. The first thing that we're going to do is finish Glow. The netlist extraction and the simulator can be considerably improved over those that we have in OCAD because we have more calibration data now than we've ever had before. So we're hoping to get Glow up to speed so that its simulator fully reproduces the performance in terms of everything measurable that we have in the GA144 at the present time. That will be a great place to move forward from. Then, since there will be no claims for ownership on Glow outside the company, we can do whatever we want to with it. And if we choose to use that as a teaching tool, for example, we can. If we choose to rent it, we can. We can do whatever we like with it. So that will be a good thing. The second thing that we're going to do is finish TCP and polyforth on the chip. It's just a matter of converting the rest of TCP. It didn't happen last time because there were other things to do. And it's a bit of a nuisance because there are so many 32-bit numbers floating around. But we will finish that and then release the whole thing in full documentation. Thank God there's a head up on the documentation because this is basically the same TCP IP package that Athena Programming has been providing its customers for 25 years. So there is a good manual to start with and edit down to one for this chip. We are going to move the development tools for the GA144 to polyforth running on the GA144. That will take care of the need for running colorforth on a PC. It will dramatically improve the bandwidth at which one can talk to the nodes, because one will be talking to the nodes at COM port speed, memory speed, not 1 megabit serial line speed. It'll be a much better and much happier programming environment, and we look forward to that because then the chip will be fully self-supporting, and that leads then to a couple of other packaging notions that we have for how to make a good development system for chips like ours that doesn't require any actual visible real computer. That can be in a little fob at the end of a USB wire, for example. So that'll be exciting. We bought some evaluation units of basic stripped down Bluetooth low energy radios last year, and we will be talking to them this year. The motivation for doing that is to find out what it takes exactly to make a minimum Bluetooth low energy stack. How much code is going to be required? Is it feasible to express that code in a few nodes or not? And this will be a big help. It's not very pleasing the way those radios are factored at the moment. Some genius thought it would be a swell idea to have a dumb Bluetooth radio communicate with us using an asynchronous serial interface with a fairly complex protocol. That's hardly an easy way for a chip with limited resources to talk to one of them, and it's hardly efficient. Just flagellating with serial line is going to be costly. But we'll work with what we have available for starters, and the goal again is to determine how difficult is a BLE stack to make. Can we put those into a chip that has nothing but F18 nodes in it without any external parts other than the radio? So those will be enough exercises to keep us mostly busy on the support software front next year. As far as hardware development is concerned, assuming that we can afford to do so, we will probably make several shuttle runs, at least 2. We have some incremental improvements to the F18, which should considerably reduced the power consumption of the chip. We found a couple of places where the existing design wastes energy flagellating high capacitance lines when there's no need to, and we will fix that. We also have learned bitterly by having programmed a lot of complex things in a chip that the real world does have events that cannot be synchronized. It absolutely does have events that have nothing to do with one another. For example, a signal coming in from an A to D that is digitizing a GPS radio for us at some frequency, and which is providing us with samples at, say, 5 megahertz, 5 megasamples a second. That is one time-based thing that's feeding us, and yet coming in from another port might be Ethernet packets that have nothing in the world to do with the time base for that charming AD. Now, to say that it was a software question to synchronize these is absurd, patently absurd. And that's what we've been telling people for years about our chips, is that you can solve all these problems by better software design. In fact, there are some problems that you cannot solve by software design alone. And what we have to do about those right now is that we have to pull the I/O register in any node that is combining events from unsynchronized sources, which eventually someone has to do in most applications where those two data have to get together in some way. Every one of those nodes that we have spinning like that is burning, 6 milliwatts, because it's running continuously at full speed. So we have a plan for ameliorating that totally. And that, when implemented, should totally get rid of spinning nodes in any applications for our chip, with the sole exception of nodes that actually have to spin in order to measure time. And we do have some examples of that. But right at the moment, say in an environment running Polyforth and running the Ethernet NIC, there are several nodes that are spinning only to solve that problem. And so we will fix that with hardware. Thank you. Another thing that we're going to experiment with is onboard SRAM. Right at the moment, we're working on compiling some, and we will find out how much silicon it takes to put a useful amount of SRAM on chip. The purpose for this would be to run virtual machines on chip without an external part. Right now, it costs in modest quantities about $12 to put an SRAM outside that we can talk to. And it costs 40 pins of our chip to do so. That's a fairly expensive price just to run a virtual machine, and yet what we're finding is that even the simplest application that a customer has come to us with requires being able to talk Bluetooth low energy out of a small device. And in order to do that, well, at the moment, we would need most likely an external memory to run a virtual machine that would deal with the protocol. The next step is to try doing that with on-chip resources if we can. If it's feasible to do that and still have a viable chip, look at what we gain. And we gain 40 pins that we do not have to commit to external memory. We don't have to commit them to parallel ports. And so, as part of that exercise, if we do decide to put a type of chip with internal SRAM, we will also make our I/O pins programmable in function, so that the 40 pins that are currently, 36 of the pins that are currently used only for two 18-bit parallel ports can be reconfigured in software to be 36 independent GPIO pins. We may also generalize the GPIO pins to be able to control saturation current both on the PNN devices. If we do that, that makes every pin into a bidirectional DAC. At the moment, to put out a voltage, we have to basically have a resistive load. If we do this with a bidirectional DAC, we should be able to have a voltage output that depends actually on an external capacitance, not an external resistance. It's still not perfect, but it's an improvement in how much power it takes to sustain an analog output voltage. And at the moment, if we want to put out an analog voltage that's measurable, we are continuously sinking current through that resistor. One can think that, for example, with a capacitive load, we could make a DAC that was simply closed-loop control of the voltage on the capacitor using the AD. And doing that, then we would have the whole thing tied down. So that's an avenue that we want to go. Mainly, we would like the chip to be configurable to have a great deal of dedicated special purpose I/O, general purpose, if you will, but special purpose for the application, independent of the use of parallel ports, and still be able to run high-level protocol code. We think that may be an important improvement in the usefulness of our chip. And of course, being that there would be enough memory to run virtual machines, that means that our chip could run Forth or C or anything else that someone wanted to make a virtual machine for. And so that is one of the reasons why it's important to us for Charlie's project to go to completion, so that we can show people eventually on one of our chips without anything else the ability to run C code in a practical way. So by the end of the year, it is our hope that we will have some prototypes of interesting new chips, possibly even a 32-bit engine, and that we will have the software capacity to program our chips in high-level C. We will have gained the ability to telnet into one of our evaluation boards and program the chips on it with no other external tools than a telnet file. Well, that's the goal for next year. I hope that I can stand up before you in November of 2015 and A, still be alive, and B, be able to say that we succeeded at those things. I wish you a pleasant afternoon. This is going to be interesting. I'm looking forward to hearing Daniel's paper. I warn you, if you have not read AppNote 7 on the Ethernet NIC, Charlie has some copies of it in paper. At least I mailed them to him, and we should have them before he gets from Bay Area. And if he does have those copies and you have not seen that document, I urge you to scarf a copy and read it during breaks, because it is an interesting piece of work. It's probably the most complex, most elaborate, and most demanding real-time application that anyone has programmed for their chips. Certainly it's most demanding that we've done. It demonstrates beautifully what we can accomplish with pipelined architecture and parallel architecture on a chip such as ours. It's something that I don't think anyone has ever done before, a bit-band Ethernet NIC. And I don't think that it's something that's practical for anybody to do with existing hardware other than computers that we've designed. So I think it's worth taking a look at. I am certainly not going to try and make a presentation of that paper here, because it would take all afternoon. It's 33 pages of substantive writing. So I'm expecting that when Charlie has me slotted in for this, what I'm planning to do is to do Q&A on it. If you have any questions about that paper, please have them ready. In fact, if you have the wherewithal to email them to me at greg@greenarraychips.com during the meeting, please do. It's always better to have questions ahead of time to be sitting there with a prepared answer rather than having to do it off the cuff. At any rate, I think it's a very interesting application. It was a hell of a lot of fun to do, and I love sharing it with people, and I'd love to answer questions about it. And now, the floor goes back to Charlie. Thank you very much. Good afternoon. I'm Greg Daly, and I am here to briefly summarize the activities at Green Arrays for the past year and to give a preview of what we anticipate may happen during the next year. Last year, we announced that we were engaged in an ASIC project for an unidentified customer and an unidentified purpose. This ended up consuming the time of Chuck, Mark Snyder, and me from about September of last year through February. It consumed Mark and me for several more months until about July of this past summer. It was an interesting project. It never led to silicon for interesting reasons. The main reason being the market in which we were engaged.
There you go. But still, I'd like to get that turned off.
Yes.
Let's see. F11. Where the hell is the... There it is. Okay. Slowly move over there. At least get that. Now, why doesn't it... What? I'd like to get rid of it.
Snoopy was a port
Okay.
I will always remember the the strip
Oh, let's
where
see, wait a
he's sitting on top of his doghouse.
Maybe one of these guys.
Shaking his fist saying, "Reverse to Red Baron."
That's this. Okay, I think the video's gone. No. Yeah, thanks. I'll get the mic on in a minute. Franklin, would you mind if we did Daniel's first and then have you, because this is a fixed time and we'll know better how much time we have to do things. Okay, so next thing, it's okay? Next thing we'll do is, next thing we'll do, well, okay. I'm sorry, I'm thinking while I'm going. Next thing we'll do is play a video that Daniel Colney provided. It's about his app note. The, let's see, it was called the Incremental PID Controller for a Brush DC Motor. And I guess I'll just run it, okay? And maybe after that we'll have a break. It's about a 35-minute video. Does that sound okay? Okay. Then, here's what I'm going to do. I'm going to make it easier on myself, maybe, by getting rid of this one to start with. Or will I? Why is that mouse so hard to find?
Gods are punishing you for your...
They are. Is it down there?
See it. Maybe you have to go up on the screen and then... Oh, there. It was there.
There it is. We got it. Okay.
There we go.
And I don't know how that happened, but what I'm going to do is just close this. Okay. That was the most awesome play in the whole World Series, by the way. Game 7, that double play. Okay. So I'm going to start Daniel's as soon as I find the mouse over here. Yep.
There we are.
Oh.
Set. The mobile robot concept.
I'm going to start him over. I'm sorry because we missed. Or maybe I'm not.
Motors, sensors, some proximity detectors, and communication system. All these parts are controlled with a single MCU running one control program. No parallelism is possible except for time-sharing multitasking. Unlike a robot with a single MCU, GA144 allows to dedicate individual nodes to specific tasks. A bunch of nodes then functions as a control module. The encapsulation of the internal function of the module simplifies the assembling of the modules together. The modules communicate via wire nodes or using a message passing mechanism. The interconnected modules then form the whole controller. The advantage of such a control system lies in its extreme flexibility. Any change of the architecture required can be done in software. We can even change the internals of the control system on the fly as the conditions are changing. GA144 also provides a true parallel computation. A robot with the differential drive has two motors with control modules. For the rest of the control system, such a module is like a black box. The only input to the module needed from the outside is demanded speed. The module then sets the driving voltage to the motor, usually as a PWM duty cycle, and checks the actual speed of the drive wheel using incoming pulses from an incremental encoder. The control process itself takes place inside the module, and the outside system does not need to know how this is done. The only output from the module to the rest of the control system is a distance traveled so far. This modularity allows development and testing the code without the real robot. Instead, an evaluation board or even SoftSync can be used. We do not need to write a special code to test our module. Green Array's IDE already provides all we need. In a sense,
testing the module is equivalent to testing a new word in Forth. This is what is great about GA144. We can use IDE to reach inside our module to change its variables and even the code while it is running, since everything is stored RAM. The subject of this talk is the motor driver module. The entire module consists of 4 nodes. The nodes 317 and 217 are used since they both have access to the GPIO pins. The node 317 uses this pin to provide a PWM waveform to drive the motor. The node 217 uses the pin as an input of a signal from an incremental encoder. The other 2 adjacent nodes implement a PID regulator and an odometer. Except for the driver node, all other nodes are suspended in reading ports. The driver node's program is composed of an endless loop performing 3 tasks: measuring time intervals, passing data between adjacent nodes, and PWM waveform generator. The 2 values on the stack are the generator counter and the duty cycle. Depending on the duty cycle, the output pin is driven either high or low. The time intervals are measured using a free-running timer. In each cycle of the loop, a counter variable CNT is incremented with the word CNT+. The timer counts up to 1 FFFF hex and stops. There is no rollover of the counter. The word CNT0 is used to clear the timer. The code within the loop also tests both right and down ports for any activity from the adjacent nodes. It is done by reading the I/O register. Shifting its value left 1 bit at a time changes the sign bit. Since the activity flag is either 0 or 1, the value must be inverted before each bit is tested with the -if instruction. The content of the I/O register is copied onto the stack. All 4 bits are tested consecutively. If set, the corresponding code is carried out. We will discuss this part of the code in more detail later. After the last test is finished, the value is dropped from the stack. The node 217 is waiting for a signal from the encoder. It reads the left port and suspends until the level on the pin is as specified by the wake-up bit in the I/O register. Setting the bit to 0 makes the read suspend until the pin is high. When set to 1, it suspends the node until the pin is low. We are now ready to follow the flow of signals between the nodes. We will see how individual nodes come from the suspended state upon activity at a port, what code is executed as a response, and when the nodes suspend again. A burst of activity in suspended nodes starts with the detection of the falling edge of encoder pulse by the node 217. The node wakes up and is about to read the current time value from 317 via the down port. Since 317 is not writing to the port yet, 217 suspends until the data is ready. Meanwhile, the node 317 tests the right and down ports for any activity. Finding that the node 217 wants to read, it writes the current timer value to the down port. This is the exact moment when the timer counter of 317 is reset to 0. The current timer value is passed through a filter to remove noise. We will say more about the filter shortly. The filtered value is then written back to the down port. As the node 317 is not ready for reading, 217 suspends once again. The node 317 needs to go through the port tests again to find out that 217 has something to write to the port. The node 317 reads the value from the down port. The node 217 then sends a signal leftwards to the node 216, where an odometer is implemented. Writing to the right port of 216 wakes up the node, and it increments an odometer counter. 1 little step of the robot is thus recorded. The node 217 performed its last action and it goes back to the suspended state while waiting for another falling edge of the encoder signal. Let's see now how the node 217 implements all its tasks. From the preceding description, we know that the code runs in an endless loop. It is implemented in the word go, which calls repeatedly the word edge. The word edge uses the leap-then control structure. When the word leap is encountered, the execution continues beyond the corresponding then. Upon reaching the written instruction, it goes back beyond the leap word, and the code is executed again. The execution of the word edge starts by putting 800 hex onto the stack and leaping forward. The value from the stack is stored into the I/O register. In the present case, it sets the wake-up bit to 1, and therefore the following reading of the left port suspends the node until there is a logical low on its pin. The value read from the left port is dropped from the stack immediately, as required by the design of the F18 computer. Then the execution of the code returns back beyond the leap directive. There are two words to be executed: EMA, which stands for an exponential moving average, a type of infinite impulse response filter, and odo, meaning the odometer. The exponential moving average is calculated according to the following formula, where I is the input signal, O is the output signal, and W is weight, or a smoothing factor. In our case, we use quite a strong factor of 0.9. Smooth signal with low noise level is necessary for the calculations used in the PID regulator, as we will see later. The effect of applying the filter on noisy data is shown in the graph. We will see later how the odometer implemented in the node 216 functions in detail. For the time being, it is sufficient to know that the signal for the odometer is an arbitrary value sent to the node 216. Hence, the top of stack is duplicated and written to the right port. In order to implement the EMA filter, we need some auxiliary words. The first word is a simple 1+, which increments value in the D register. The next one is a fractional multiplication with rounding star.r. The word calculates with fractional numbers, where the 18-bit value is a signed number in the range from 0 to 1 exclusive, with the MSB being the sign bit. As the calculations are valid for positive numbers only, the MSB is always set to 0. The word star.r expects a positive fractional multiplicand in the S register and a positive integer multiplier in the T register. The multiplier is moved to A and T is set to 0, the initial condition required by the word +*. The multiply step is called 17 times within a 4 micronext loop. The product is a 36-bit number with a 17-bit integer part in T and an 18-bit fractional part in A. The bit T17 is a sign bit and is always equal to 0. The bit A17 is the MSB of the fractional part and it represents the value of 1/2. The rounding takes into account the value of this half bit. If set, the integer part in T is incremented by 1. Otherwise, it stays unchanged. We are now ready to explore the calculation performed by the word EMA. The word expects two values on the stack, a weight W in S and the last output of the EMA filter O' in T. Out of reset, these values are set to 0.9 decimal for the weight and 1 FFFF hex for O', which is the maximum positive number. Calling star.r, we get a product of the weight and the last output in T. Note that the value of weight in S stays unchanged. Next, we copy the weight on top of stack, and the following code calculates the required expression 1 minus weight. Now comes the part when the node 217 reads the current value of timer counter from 317. The A register is loaded with the address of the down port, and a fetch instruction gets the input data from stack. The second star.r instruction then calculates the product of the input value and its corresponding weight factor. We get rid of now disposable factor from S and sum the two products together. The resulting output value is duplicated to be used during the next execution of the word EMA, and it is written back via the down port to the node 317. Note the two instructions moving data between the nodes 217 and 317 being in part of the word EMA. The last part of the word edge is used to get past the rising edge of the encoder signal. A zero value is stored onto the stack, and the execution of the following code is repeated. This shows how the lead-then control structure can be used to shrink the code. Since this time the wake-up bit is set to 0, the left port reading suspends the node until the level on the pin is high again. This ends the execution of the word edge, and it returns back to go, which restarts the whole loop again. Now we can finish the discussion of the code in the node 317. We already know that this node is constantly executing a timing loop. We also know that within that loop, the right and down ports are tested for any activity. In order for the loop to be running uninterrupted, a temporary storage for data being passed between nodes is needed. Such a buffer is defined by the words buff and buff store. This code shows a way of defining variables in array form. There is also a third word, buff0, which is used to clear the buffer. After incrementing the timer counter by calling the word CNT+, the content of the I/O register is put temporarily in T, and the bits corresponding to the activity at ports are tested as discussed earlier. In the following, only the code enclosed within the -if-then clause is shown for the sake of clarity. Although the bits are tested in the order given by their position in the I/O register, this is the right port before the down port, we will start with the down port, as this is the port communicating with the node 217 already described. First, the A register is loaded with the down port address. In case the node 217 is suspended while reading the down port, the current timer counter value is written to the port, and the counter is reset to 0. If 217 is suspended while writing to the down port, the value is read from the port and stored into the buffer. When testing the right port activity, the A register is loaded with the right port address. In case the node 316 waits suspended while reading the right port, the value stored in the buffer is written to the port, and the buffer is cleared, unless it is already equal to 0, in which case nothing is written to the right port, and the node 316 stays suspended. Thus, only a valid timer counter value stored in the buffer is sent to the node 316. The sequence of directives ahead swap then, in the colors shown here, enclosed within the if-then directives, functions as an else directive in the standard if-else-then control structure. In case the node 316 waits suspended while writing to the right port, the contents of the T and S registers are temporarily stored on the return stack. The right port is fetched, and the two values from the return stack are moved back. The net result of this operation is that the PWM generator increment is replaced with the new value provided by the node 316. There are two subtle points to be clarified. The first is the content of the buffer buff. We have already shown that between two consecutive falling edges of the encoded signal, the timer loop makes a certain number of cycles. The longer the interval between the edges, this is, the slower the movement of the encoder, the higher the number of cycles counted. It follows that there must be a minimal number of cycles counted, and that this is a non-zero value even at the maximum speed of the motor. Thus, a zero stored in the buffer buff is a flag notifying the system that the node 217 is still waiting for the falling edge of the encoder signal. As we showed earlier, the whole process of reading the timer count is started by a falling edge of the encoder signal. However, what happens in case the signal from the encoder is constant, for instance due to the fact that the motor is halted? In that case, the timer would run up to 1 FFFF hex and the whole controller would become deadlocked. To avoid this fatal state, the code for the word CNT Plus needs a little modification. Instead of dropping the overflown value 20,000 hex, it is inverted, resulting in 1 FFFF hex, and it is stored into the buffer. The buffer now contains a non-zero value corresponding to the maximum time interval that can be measured by the timer, even if there was no falling edge of the encoder signal. And this value can be passed to the node 216 when demanded. This keeps the module responsive and under control of the higher level program. The second modification is aimed at reducing the energy consumption in cases when the module can be stopped entirely. Such a situation occurs, for instance, when the robot halts. With the code already presented, the timer and PWM loop is constantly running, even if zero speed of the motor is demanded. The modification exploits the fact that the PWM increment may be a positive number only. Therefore, we use a negative number as a signal for the node 317 to stop the PWM generator with logical low level set at the output pin and to stop the timer loop. We define a new word, PWDN, which stands for power down, starting in the middle of the test of the right port being written to. After the contents of T and S registers have been stored on the written stack, the value from the port is fetched. Upon fetching the value from the right port, it is tested with the -if test. If negative, the value is dropped from the stack. 20,000 hex is written to the I/O register, driving the output pin to logical low, and the execution jumps to the beginning of the word power down. Here, the node 317 wants to read the right port again. Until there is a new value provided by the node 316, the node 317 stays suspended while reading the right port, and the energy consumption drops to its minimum. To wake up the node 317, it is sufficient for the node 316 to write a positive value to the right port. Upon that, the value is read by the node 317 as a new PWM increment. The two values from the return stack are moved back to S and T registers, and the node 317 continues executing its code. We shall now examine the node 316. Out of reset, the node is suspended in reading data from 317. The data provided by 317 is the filtered value of timer counter, which represents the current speed of motor. In the following part, we will be referring to speed of motor expressed as the number of timer cycles between two consecutive falling edges of the encoder signal. Strictly speaking, this quantity should not be named speed, as the relationship between the rotational speed of motor and this quantity is inversely proportional. However, we use the term speed here for the sake of simplicity. When the node 317 finds out that 316 is waiting suspended to read the port, and the current speed is available in the buffer in 317, it writes the speed to the right port. 316 then performs PID calculations and is ready to write the updated PWM duty cycle back to the node 317. The 316 then suspends until the node 317 is ready to read the data. Following that, the node 316 checks its left port for any message waiting. If there is a message, the node reads it, and based on its content, other actions can be taken, such as the demanded speed updated. Finally, the node suspends again while waiting for another speed data from the node 317. We shall now examine the code for the PID regulator. The theoretical background of the PID regulator is described in the corresponding application note AN016 and will not be presented now. The PID controller requires two input quantities as explained earlier. One is the demanded speed, Wk, the other is the actual speed, Yk. The indices k emphasize the fact that discrete quantities measured at a data point k are used. It is similar to a t-index used when continuous quantities at a given time are referred to. The regulator calculates a difference between these two values as an error Ek. The output of the regulator is called the control function Uk, which in our case is a PWM duty cycle for the node 317. The calculated Uk is such as to decrease the error to 0 as fast as possible and keep it there. The incremental PID regulator does not calculate the current value of Uk. Rather, it calculates an increment to the control function delta Uk, which describes a change needed for the Uk to reflect the current error Ek. Note that the value of delta Uk is signed and can be either positive or negative. The calculation is carried out according to the following formula, which describes the discrete incremental PID regulation equation. The symbols Ek, Ek-1, and Ek-2 represent the last three errors. The equation thus takes into account the recent history of the regulated system. The symbols Q0, Q1, and Q2 represent three parameters that have to be found experimentally in a process called regulator tuning. In our system, the values Q0 and Q2 are positive numbers, while Q1 is a negative number. The code for the node 316 starts with a definition of a double precision variable U. The variable is defined as two single precision variables in the node's RAM. The high part of the variable is defined with the words uHigh and uHigh store. Since we need to access the same word in RAM also in the extended arithmetic mode, we defined other two words, extended uHigh and extended uHigh store, with the extended arithmetic mode on. The difference between uHigh and extended uHigh is that when the latter is called, the extended arithmetic bit, this is the address bit 9, is set to 1. Otherwise, it is cleared. The low part of the variable u is accessed in the same way using the words ulow and ulow store, or extended ulow and extended ulow store. Next, we define some arithmetic words. The increment 1 plus, and an integer multiplication star. This word expects two 18-bit numbers in T and S. After the multiplication has finished, the 36-bit long result is stored in T and S, with the high-order word in S, while the multiplicand rests below it on the stack. Finally, we have a word MAC, which stands for multiply and accumulate. It expects two 18-bit numbers on the stack, a positive multiplier in T and a signed multiplicand in S. The result of the multiplication is added to the variable U. Note that this word is also defined with the extended arithmetic split set, hence the additions are carried out in the extended arithmetic mode. The heart of the regulator code is defined in the word PID. It expects two older errors already on the stack and the current speed in T. Its execution starts with fetching the value from the address 13 hex, which is a memory cell containing the demanded speed -1. The following instructions then calculate a difference between the actual and the demanded speed, the error EK. The following three lines of the code calculate successively three terms of the regulation equation. The three constants are the optimized parameters Q0, Q1, and Q2. First, Q0 times EK is calculated and added to the variable U. The error EK is temporarily stored on the return stack, and EK-1 is negated. Next, Q1 times minus EK-1 is calculated and added to the variable U. The error EK-1 is negated again and stored on the return stack. Finally, Q2 times EK-2 is calculated and added to the variable U. The two errors stored on the return stack are moved back. The variable U now contains an updated value, and three latest errors are on the data stack. Note that with each calling of the word PID, the errors are pushed one position down the stack and never removed from it. Here we have another example of how clever is the design of the F-18 computer in using circular stacks. The following part of the code is intended to get the updated U function within acceptable limits. These limits are given by the range of the PWM duty cycle. This is from 0 to 1 FFFF hex. First we test whether the new U value is negative by testing the sign of its high-order word. In such a case, the control value has underflown and is set to 0 as the lowest possible value of U. 0 is also sent back to the node 317 as the updated duty cycle. If positive, the high-order part of U is cleared and the low-order part is tested for overflow to the bit 17. If overflown, the value is set to the upper limit of 1 FFFF hex. Otherwise, the calculated U is within limits and is sent to the node 317 via the write port. The code in the node 316 begins execution at start. It just clears the carry bit of the extended arithmetics and falls through to go, which is an endless loop. In the loop, the node suspends while reading the write port. It stays in the suspended state until the current speed is sent by 317. With the current speed in T, the word PID is called, the updated duty cycle for the PWM generator calculated, and sent back to the node 317. What follows is a code for reading modified ganglia messages. It tests the left port for being written to. If true, the execution from the left port is called. Otherwise, the loop returns to go. The modified ganglia messages are described in the application note. It allows to set the demanded speed by writing to the address 13 hex. It can also be used to read the value of the control function U, the latest error EK, or even to set directly the PWM duty cycle, and so forth. It is also used in sending the power down signal to the node 317 in the form of negative PWM value. In general, the code via the left port can read or modify any RAM location or even the values on both stacks. This demonstrates the true power of port execution, as all these tasks can be carried out while the whole motor control module is running and performing its duties. We have already seen how the node 217 writes to the left port as a result of a falling edge of the encoder signal. This wakes up the node 216 and an odometer counter is incremented. We shall now inspect the code of the node 216. A variable auto holds the count of falling edges of the encoder signal. This number can be easily converted to the number of motor revolutions and therefore to the distance traveled by the robot. The word auto plus is used to increment the variable auto. The main code loop is defined in the word go. The A register is loaded with the address of the right port and the register B points to the IO register. Both values are set in a boot descriptor. Fetching from the right port then suspends the node until the node 217 writes to the port. The value read is left on the stack as it is a dummy word. The counter auto plus is incremented and the code tests the IO register if the left port is being written to by the node 215. The left port is an entry point for a ganglion message. If active, the first word from the left port is read, which is a focus call whose execution we want to avoid, and then an execution from the left port is initiated. The ganglion message can be used to read the content of the counter auto or to clear it by writing a 0. When finished, the execution returns back to the word go. And so we have covered the last node of the motor control module. At the beginning of our presentation, we have explained that a mobile robot needs two motor control modules in order to provide a differential drive. We have explored the module internals, and we should now look at the possibility to place the modules inside the GA144 chip. The module for the right motor can be placed in nodes 217, 216, 317 and 316 as shown earlier. The second module can be conveniently placed right above the first one in nodes 517, 516, 417 and 416. Note that the second module is a mirror image of the first one and is symmetrical along the line between the rows 3 and 4. Thus, the motor control modules form a cluster near the right edge of the chip. The communication ports to the modules are located on the left side of the cluster and therefore are accessible from Polyforth, for instance via Ganglia message or from the Green Arrays IDE. In order to demonstrate that almost any code for GA144 can be developed and tested in the software simulator, we are now going to show how the whole module runs in SoftCell. For this demonstration, we have used a testbed providing a square wave signal which simulates pulses from an encoder. After initialization of all nodes, only 317 is running, while the other 3 nodes are suspended reading from ports. The PWM generator is toggling the levels on the output pin. The node 217 waits for the falling edge of the encoder signal. When it comes, the node starts executing until its result is passed back. Then the odometer receives a signal and wakes up. Next, 316 reads the speed, calculates a corrected duty cycle, and sends it back. The burst of calculations has finished, and except for the timer and PWM generator, all the nodes are suspended. There is a short wake-up of 217 when a rising edge is detected, and then it awaits a falling edge in the suspended state again. We now accelerate the video 4 times so you can appreciate the time distribution between executing and suspended state in nodes. Watch how a falling edge on 217 starts the burst of action, which is quickly replaced by a longer period of inactivity. No experiment can be entirely replaced by a simulation. Therefore, we have carried out a series of tests with a green erase evaluation board controlling a brushed DC motor. We have used an optical encoder and an electromechanical brake controlled by a polyfold program. The setup is described in detail in the application note. The experimental run consisted of several steps. First, the motor was started and its speed stabilized. Then the control program written in polyfold counted 8 encoder wheel revolutions and a signal was sent to the brake. The brake was activated for another 8 revolutions and then it was released. The last part took another 8 revolutions and the motor was turned off. There were 2 rounds of experiments. First unregulated with the PID regulator off, the second regulated with the regulator on. During each experimental run, the actual speed of the motor was recorded. The result of the unregulated run is shown in an orange trace. A dramatic decrease in speed is shown when the brake is applied. The speed increases incrementally after the brake is released. On the other hand, the regulated run shown in a green trace demonstrates clearly the regulator in action. The speed of the motor is almost constant, slightly oscillating around the defined set point. We have confirmed our design experimentally. I would like to thank Green Arrays for their support, particularly Greg Bailey for providing me with the evaluation board and Charlie Shattuck for invaluable discussions about programming GA144. And thank you for your attention. Building a GA144 controlled robot, taking the first step. The mobile robot consists typically of several parts. Power source,
Thank you, Daniel. Now, yes. How did we get his picture up here? I should have asked you that a long time ago.
Without him on,
Yeah.
share your account, get him onto the video live.
I'm sorry I didn't pursue that earlier. Okay, we're
This
getting.
is
Oh,
always an experiment.
yeah. So we're going to take a minute or two to get Daniel's picture up here where all of us in the room can see him. And I hope maybe you'll have a question or two for him to make it worthwhile. There's no way he's going to be up here, huh? Is that okay? Yeah.
We can actually see that. Because otherwise, it's just you and I can see. I know.
There we go.
Sure, great. I'm going to do some questions and answers first.
Well, Daniel's here. We'll do this, and then we'll take a break when Dan. He is. He's in the Czech Republic. We can see him on this computer, and soon we'll see him up here.
He should unmute himself. Stand by. No, he's still muted in Hangout. I don't see anything muted. There he goes. No, I was the one that was muted. Oh, that's right. That's you. Yes.
And there's Daniel.
And there it is. Now we don't hear him say that.
We don't hear you yet, Daniel. Hang on.
Can you hear me now?
Negative.
Okay.
Say something. You're alive.
My microphone is working, so can you hear me now?
Yeah.
Yes.
Yeah.
Hello?
Do you hear us? I can hear you.
Okay, great.
So, anybody have a question? Keith?
Yes. Josh, can you hear me? Do I need to move somewhere else?
Can I go over there? Talk to my chest.
Camera. So, I mean,
Okay,
is there a place where it can be squared? It's getting there. Hi, great demonstration video, and I noticed at the beginning of it that you showed a two differential wheel robot, but you only showed a test fixture that proved that the motor was capable of operating with stressor conditions with the brake. So we never saw the robot move, and I want to see a robot.
Okay, thank you. I can explain that. Actually, when I started this work, I didn't think about robot. And I started the application node just with one motor and wanted to show the PID regulator. But then I realized I can put two such modules onto the GA144, and actually that this could be the first step to building this robot. So what you've seen is that's the reason for the title, taking the first step. And there I hope will be other steps, and at the end there should be a robot.
Okay.
Driven by GA144.
Thank you. Anybody else? James.
For the EWA weight value, did you consider using an easier number than 0.9, like 7/8 or 15/16?
Yes, actually 0.9 was the lowest value that really worked, because the signal is quite noisy. And as you have seen, I calculate the difference between set speed and the actual speed. And if the signal is noisy, I get very random values, I would say. It runs up and down. So it is really important to have a rather filtered signal from the encoder. The reason is that actually the PID calculations are based on derivation. And that would be difficult to calculate with noisy data.
Thank you. Anybody else? I guess no more questions.
Okay. Thank you very much. Thank you. I'm glad I can be with you at least like that. Thanks.
Awesome.
Okay. Bye-bye.
Yes, John.
Tell everybody how much experience he had in court when he did this.
I'm pretty sure it was 0.
Essentially, that much.
I think it was pretty close to 0. Franklin, you had pretty much 0 too, right? Franklin's going to talk in just a minute.
Yeah.
Daniel's a really smart guy, though. He picked it up really fast. I mean, he's going to be taking my job over as far as I'm concerned. He's great. So, let's take a short break, and Franklin will come up and talk when we're done, okay? What is it? What do you say, 10 minutes, 5 minutes? Is 5 minutes good enough? Let's take 5 minutes.
Can I borrow that USB stick again? I noticed there was a...
Oh, yeah.
Somehow you have to addressed.
Right? Sure. Thanks for doing that. I wish I'd
Yeah, no worries.
thought of that earlier.
That just goes to indicate my proof that, you know, North is one of the easiest languages to learn. Not necessarily to master, but certainly to
No. Oh, you mean about him? Yeah. Well, what I meant was thanks for getting the picture up there. But yeah. Yeah. No. I know. You need to know something else. Fourth's not the hard part.
Yeah.
Knowing what to do with it is the hard part.
That's exactly right.
Yeah. I'm gonna.
There's this just interesting how like walking by whether or not it's on here or not. Like it looks almost 2-3 miles the older yeah, it looks like it's gonna bother us both until the end. I think I updated because I was cheating. There's a installer it will see just make sure you have one. If it's the play that I'm thinking, if you're not going to make a catch, I'm not sure that's necessary. It's close enough that I'll call it that. But I seem to remember when I, I haven't seen the picture before, but it was a very dramatic place. Our setup is all except for general use. Works at all. Sure match. That's the first time overserved. Yeah.
Was that the glove Penix flip to second base for the double play?
Yeah.
Yeah.
Awesome.
Oh, that was such an awesome. I watched all the games.
I did too.
Oh man,
I really enjoyed it.
Ah.
I was texting back and forth with my son Tom too. That was really fun. Yep. But that was, and that's where they had to do the replay to make sure that.
Yes.
Yeah, wasn't that
Yeah.
dramatic?
The tag at first. Man, that was so close. And then it just has to touch the glove, you know.
Yep.
The ball touched the glove before the foot touched the plate.
Exactly.
The base.
And the foolish guy diving and sliding down the dirt. You know, probably would have made it if he'd been running.
But then there was the Giants blew, you know, with the out at first where McGarner played it through it.
I know.
To Belt, and Belt goes trying to slide into first himself.
Right, that was too bad. But fortunately, it didn't ruin things.
Yeah.
Yeah.
But I meant what I thought there should have been more errors called. There were some hits that were allowed that, yeah.
So, everybody ready to get started again? Can I get everybody's attention? Do we need to wait for Samuel? Okay, come on, cats. Just a sec. That looks pretty good. Okay. Our next speaker is going to be Franklin Amador. It's Amador, right? And he's going to talk about his exploring one-wire devices on the Green Arrays 144. I'd like to mention that Franklin is another person who had very little experience in Forth before he started. So both his project and Daniel's project will show you where you can go on this chip. Pretty much from zero. Franklin?
Oh, okay.
I can run it.
Oh, that's fine. I can do it. Thanks. So, my name is Franklin Amador. I bought the Green Erase chip development board 2 years ago. It took me a while to ramp up to speed to learning it. First thing I did was try to change something on it because there's some circuitry on note 606 for SPI chip select, and I wanted to see if I could do more chip selects with it. So I thought maybe talking to a one-wire device for digital I/O to give me more I/O chip select input and outputs. So what I did is I took, like anybody else would do, is see how everybody else is doing it. I saw Brett Rodriguez from Chemiforth doing it in several devices, so I used some of his stuff and just ported it over to the Green Arrays. Most of it ported over really nice, except for a couple things, and I had to debug. But that was on the high-level polyforth. Of course, there's nothing out there for the Rayforth for the F18A unless you port it over from Logic. So that's what I did. So this is an outline. And why did I do this? Like I said, I want to expand the I/O on 606 node for SPI, mainly for more I/O interface, and because I could. I know it's a slow protocol. Who would want to use 13 kilobits per second or something at overdrive speed of 10 times that amount? But if you're running low on I/O resources, this is a good, cheap, easy way to expand it. That's what I did. But doing this, I didn't think about this last part, but there's a lot of stuff out there for one wire. There's encryption, there's analogs, there's digital, there's communication converters, protocol converters, and memory over one wire devices. So I need a level converter between the green arrays. I bought a chip that had a pull-up resistor for this. It was too small. I couldn't solder anything to it. So I did my own circuit, but in the end, in retrospect, I recommend just using the level shifter that's already on the board itself and just add the pull-up resistors. So the protocol itself is pretty simple. There's the clock is internal to the devices. The master initiates everything. So I turn one node in the green arrays 144 into a master with this code, and basically started doing the timing. It turns out you could do a microsecond loop over I think it's 10,000 loops in a F18, maybe more. So anyways, here's the master, and here's the bus itself. And these are your samples, where you take a sample and find out if something's on the bus itself. So everything starts with a master reset, and then the devices on the bus respond with the presence pulse. So the master pulls the line low, and then releases it after a certain time, and everybody on the bus just listens to the master at that point, and they have to respond if they understood that reset pulse. They all respond with a pull down low, and basically once they do that, you take a sample and see if it's low, and if it is, then you know there's a device on the bus. So how do you write data back and forth on the bus from the master? Essentially, the master does everything. It's just a time-based system. When the master writes a low, it just pulls the line low for that amount of time on the standard speed. And then if it's a write 0 or a write 1, it just releases the line after a predetermined amount of time. Now, since the master initiates everything, when you want to read a slot from a device, you pull it low and it releases, but the device itself will keep the line low if it's going to be a 0. Or release it, and then we read it at this point, and it'll tell us it's a 1. That's when the master says, okay, I want to initiate a read, and the devices respond either with a 1 or a 0 by keeping it low. So essentially, since the master initiates everything, when it's sending data, it just outputs the data as 1s and 0s, and the devices read that data. Now, when it's receiving data, it always has to initiate the read. So it'll send a low command, and if the devices in the field keep it as a release, don't release it, then it stays a 1. But if they pull the line low, the field device pulls the line low after this initiation from the master, and we sample at predetermined amount of time, we find out what that is. So the master always has to send a initialization command of a 1. So a byte of 1s is FF. So every time you want to read something, you send FF, send. So this is the kernel I wrote. It not a lot of words, but I like the fact that I could fit it all in one node. This kernel handles the read writes along with the byte send to get the data back. Here's a delay loop. 100,000 of these, I guess I was off by 0. We'll create a 1 microsecond. Oh, sorry. Okay, 100,000 of those will create 500 microseconds of wait. So here's where I read the pin and find out if it's a 1 or a 0. I have to be able to pull the line low or high on that pin. So that's where the high impedance and low commands come in. On the reset, I start with a low, which pull the line low. I wait that amount of microseconds. Then I pull it high. I wait 15,000 delay. And I see what the pin's doing after that time. Then I wait. Now here's where it gets tricky, because when I read the pin, I do 20,000 and on that pin to find out if it's been pulled low or high. So if it's a 1, to me that's a 0. So I do a do OR. And if it's a 0, I invert it and send it back. Okay, so the slot doesn't matter whether you're reading or writing. It's always going to be the same predetermined amount of time. So always the master initiates a low. It's all delay based. So I delay this much. Usually that slot write command comes from polyforth down here. So I'm going to get a value to write to that slot. So 8-bit value. And what I'll do is I could send 1, or if I want to send a whole byte, I send it with a for loop. So that comes in handy because we're going to, at some point, read 1 byte or 2 bytes. Bits. So 1 shot gives me a 1 bit. 7 shots gives me a whole byte. So when I pull the line low and wait, I dupe what's on the stack and end it with 1, meaning I'm looking at the first bit. And if that bit is 1, I pull it high. Pull the line high. If not, then I drop it because I duped it, and I delay and then wait for the pin, what's on the pin. After that, if it's a 1 on the bus, what I do is I want to add that value to bit 8 and then right shift it. So then when I'm reading a byte, I'm getting it, adding it to the top, shifting it. Eventually, when I do that enough, it'll give me the byte that I want. Then if it's a 0, I drop it, right shift it, delay, pull it high again, and then wait. So with this, you're able to talk to all the devices. But the tricky part comes at the high level fourth that you got to talk to these devices, because each one has a 64-bit lasered address that you have to call them out to, especially have more than one. So what I wrote here was, say you're just testing the code in the kernel in the F18, then if there's no single one-wire device, then you can use this just to test out if data is going into the node or not. If there is one, then you can use this system here, where I jumped a little bit ahead here, but to run this, you need the snorkel and ganglia code that's in node 1, page 142, I believe, from the polyforth interface. So with that, once that's loaded, then you can address and talk into the node from the virtual environment, the polyforth virtual environment. So with that, I was able to talk to the node and write words that would overlap with the words that were over there. So if you notice here, the 29, 2B, and 2D there corresponds to here, where I come in with polyforth and interface into these words that'll run the data on that node. So I recreated those words up here, and then everything else that was ported over kind of works. To put a byte on the bus, that would be one wire put or one wire get, which as a get, you always have to send 11111s and into the node to send it out. So after that, after all of this was debugged, then I was able to continue and write the rest of the code. Some of it I had to modify, but eventually it came together nice. I had 2 temperature sensors in there. With them, I was able to write the code to read into 2 of the sensors, which I got their serial numbers from a search command that's in this code. I didn't put it in here. It was going to be too much to go into it, but eventually this will be published, I believe, by Green Erase at some point. And with the show IDs command, you actually get to search all the 64-bit addresses for each device on the bus. So if you have 10, 20, 30, it'll let you see what's on the bus with that. And then once you know that, you could create mapping to them and then just talk to them direct and get the data directly from them. There is a CRC feature to this. I haven't coded it, but that'll come later. I also was thinking about, this is just interfacing to the temperature, but I need to write more into the kernel to do other one-wire devices. I want to be able to read, let's say, 2 bits of data bits coming back from one-wire devices. But eventually, it worked. It compiled, and I was able to get data back when I was interfacing with the devices, both in whatever format I wanted. So that was good. Now, there's a lot more of these devices that I was anticipating, that I just wanted to see what it would take to get one to work. I got it to work. Then I realized there was like memory devices that you can talk to, security, adding more GPIO, temperature sensor, real-time clock, battery management, and protocol conversions to go with it. So there's a lot of things you can do with this now that you can interface to one-wire devices. And the applications, for me, it would be security for panels, say electrical panels. You put one of these things and talk one wire and get input devices from one bus. The doors open, somebody unlocked it, or things like that that would trigger a one-wire device to give you data, and you could add timestamp to it. The other big one would be at some point, if all the F-18s get small enough and disposable enough to be in medical devices, you could also have sensors that are over one wire and be able to give you data about a person. You know, like if you go to emergency room, they just patch you up with all these computers, F-18 computers and sensors, and then when you're done, they just throw it away. You know, I think that's where it's going to go at some point. So the architecture, after going through the learning curve, is simple and modular. Once you get to know it, porting code is easier. I'm looking at VHDL code now to port over to this because I'm picturing VHDL code to me is just hardware definition for what you want. That's what F-18s look like to me. They look like logical units, versatile logical units. So if you could have a VHDL to F-18 compiler, you could convert all that hardware that do audio, video, anything, any of those that are already open source, you know, like open course. I think it would be a good thing. The last thing is, it was already addressed. You know, it was my hope at some point either port array forth into polyforth or vice versa, so that you could have one interface for the whole thing. And it seems like they're going to go that way. It didn't matter to me which way they went, but we'll see how it ends up. And there's data there for if you want to look at the whole write-up. You go to GitHub. Eventually, I'm going to delete that because Green Erase will take over. And these are references. If you have any questions, let me know.
Okay.
Yes.
Is one wire standard a single frequency or the multiple frequency?
Standard for their standard is 16 kilobits per second. How do you do this? Oh, sorry. Yeah, the standard is this much, and it's all time-based. It's predefined. They have a window of like, oh, if you want to do a reset pulse, you got to be within these parameters so that the timing and the slave devices know what your intent is from the master. And the time is all internal to the devices. There's no clock, except for what the loops, all these things are doing. And then there's a feature for some that are in overdrive mode, that you put them all in overdrive, you could talk to them 10 times faster.
Do you know how they picked that frequency?
I do not. The standard, it came out, and I think it stuck. I looked into it, but most of what I was reading is like if you have a 250-foot cable and you have multiple of these on there, what kind of noise signal you're going to expect. It could certainly change, but it seems slow enough so that you could do other things while this thing's sending data and receiving data in between slots. Because in the end, I was told, why would I want to do this if it's so slow of a protocol, you know? Well, because I can't, but I wanted to see what it would take. And it turns out it is a slow protocol. I could do 100,000 things with F-18 in one slot.
Anything else? Frank?
We'd like to get Greg up if possible. I saw his face there. Yeah, there he is. We're going to fiddle a bit more and get Greg. Yeah, get Greg Bailey up on the screen. You ready there, Greg? It'll just be a minute.
Was that? Yes.
This isn't muted, is it? Actually, I thought. Come on. Okay.
Of course, I can't see who's asking questions, nor can I hear them. I hear no audio from there at all.
Hello there.
There, I hear something. Evidently.
You want to say something, Greg?
Yes, something.
There he is. There he is.
Well, the nature of the beast here is ask me anything. I'm going to pretend I'm Richard Feynman. Specifically, though, the topics would be App Note 7 on the Ethernet and the remarks about the recent and future activities of green arrays. And I honestly can't hear anything from the room except Charlie now speaking right up against the PC.
We're doing wrong, guys. Actually, we don't. Can we get it through your microphone?
Okay, that feedback is all happening there. I turned off my mic and
Can we get it through? My microphone does not work for some reason. I don't understand why. Okay. No, it won't be through your microphone.
all right, I didn't hear any feedback on that.
Your system. Yeah. So we're getting his microphone coming in. All that you're doing is turning on your speakers to go there to the in-house speakers.
Correct.
So you have Gregor speak right now.
Speak right now.
No, we have not. Turn down. That's turned down. That's why. To turn this up? Yes. Try. But I mean, that's. So you need that. Well, you're gonna that thing.
Did you make this work with Daniel? Suggestion, in order to get moving, if anybody's got a headset there, why doesn't somebody plug in a headset and just reiterate any questions?
We'll turn this on and off so that you hear us. Could you say something? Start speaking, Greg.
I'm starting to speak. I'm continuing to speak. I am still speaking. I'm scratching my lip. Okay, more speaking. More speaking, more speaking. Okay, I see a thumb. Whoops. Are we ready? Well, in that case, does anyone have a question about the Ethernet interface or about green arrays or anything like that?
Looked like I was raising my hand, but you know.
Okay.
Well, I do. Nobody else does. It's Mark Flamer, Greg. Nice to
Hello, Mark. Yeah.
Nice to see you in person. Well, I was excited to hear about the potential of maybe having some SRAM on the GA144, and I'm sure that's off in the future at some point. But I'm just curious if there was anything more you could follow up with on that. Have you done any preliminary calcs on what you could fit on there, or whether that may be a reality in a year, or?
It's entirely a question. In this case, the available dense SRAM, denser than we know how to lay out, or certainly denser than we can within the design rules, is commodity SRAM from ARM. And we finally scared up a Spark workstation, which is yet to be fired up, but at least it's here now. And ARM has such disdain for 180 nanometers that they haven't bothered to update their SRAM compiler to run on anything other than a Spark workstation. But when we have that running, then we'll compile some and find out what kind of form factor it's got and what kind of interfaces for what kind of density. And then we'll have some idea of how much of a chip we can build around one of those SRAMs and still have a reasonable die size. It should be incredibly efficient to talk to, because instead of multiple picofarads per pin of capacitance to charge up when we want to talk to the damn thing, as I recall, when we had some compiled before, it was almost single-digit femtofarads for the interface pins, which is a lot more pleasant kind of a thing to be driving. And they should be quicker. And of course, if the SRAM is on chip, then we know what we're talking to. And so there's no reason to have a general purpose SRAM interface. We can go ahead and build an efficient hardware one, and that'll make the thing at least 10 times faster to talk to than what we have now.
Thanks, Greg.
Thanks. I'm highly suspect that at least some people here would like to see green arrays to actively go forward, earn some markets, increase capitalization, etc., etc. I'm trying to figure out what those problems which prevent quite from doing so. What are, I mean, there are brilliant scientists, brilliant technologies over here. Did you, for example, try to, I mean, if I would like to create my own small social media network with for people who like to discuss cats, I would probably go at some point to startup incubator, to ask, would you help me to develop my business?
All these people that do that for a living want 20% of your business.
Try to think along those lines.
Okay, to begin with, people that do that want a major ownership.
We have your voice turned down, so hang on. You're gonna have to start over when I turn this off. Hang on.
All right. Yes, but the issue is not one of smoke and mirrors. We had smoke and mirrors guys working with us in Intellisys. They got us a shelf of trophies from magazines for design awards. They didn't get us a single contact from a credible customer. But these were highly trained, highly track recorded snake oil salesmen, and they did a fabulous job. But what we need is customers. We don't need snake oil. We need money. We don't need people who will promise to find us money. We've had those too. People that are in the business of helping people that don't know what the hell they're doing, like us, make businesses, want a big piece of it, and they want a lot of money out of the deal. And that's all very nice, but somewhere along the line, letting somebody like that have control over the money flow is going to determine what it is that we actually make. Now, none of us came here to have a repeat performance of what has happened in the past. And that is when we set out to make something, and then you find out that the people that are going to put money into it want you to make something completely different. That's the big problem that we have. Right now, if we had even the dough for all of us to be out making sales calls on people, that would be a great improvement. But we don't need any trophies, and we don't need magazine articles that are not backed up by customers calling in and wanting to evaluate our hardware. And that's what that path does not necessarily lead to. Social media, same thing. We've had a lot of social media things happen, but honestly, the most productive thing that happened was when one of Mark Smader's sons made a post 2 years ago on the Y Combinator Hacker News group. And we actually got 3 calls from people who had businesses that could conceivably use our chips. Unfortunately, the architecture of our chips didn't match the goals of 2 of them. And we keep repeatedly hitting this barricade that very few people have got a tight enough control environment that all they need is rapid flow of data processing. They eventually end up needing to talk to something. By the time you put enough F18 nodes to work trying to talk to something, you still don't have a full protocol. Try doing DHCP in one of our chips with just node code. It's already an incredibly complicated protocol for nothing more than getting an IP address. So from what I've seen in terms of people that asked us about possible applications and what we didn't have for them, the SRAM is the key thing. Now there's a question up here about EEPROM. We looked. There is a sort of flash which our foundry makes available as part of as an option for our process. The trouble is that it's huge, physically huge. It requires building multiple independent wells for the flash. It involves building a plus and minus 7 volt charge pumps and an onboard supply for that stuff. And it's only good for 100 cycles of write. So very limited use. To serve the same goals as an external SPI flash, it wouldn't, because the external SPI flash is good for far more write cycles. The only thing that it would be good for is putting a single program into the chip and being done with it. Well, it's simpler. It's simpler, as Daniel inquires. It's simpler, but it's also extremely expensive of silicon and expensive of complexity to put this flash on there, and then to have it end up being of such limited use. The next thing somebody would want to do is use it for non-volatile memory. And even for the kind of non-volatile memory that you need in, say, an ink cartridge on a printer, those things have more than 100 cycles of on-off in their lives. So you couldn't even use it really for that. And naturally, if you wanted to have independent sectors for erase and write, then you have to build independent wells. And the thing gets even bigger. So it looked to us like a nightmare. The SRAM is less of a nightmare as far as I can see, but we'll find out more. It may be that it's not of a viable size, but if it is, it's an awfully attractive thing to do for all the aforesaid reasons, pins and functionality.
Great, we're doing this half duplex. You're turned off now. We've got another question, and when you hear some silence, I will turn this off again and you can talk again, okay? Here you go.
Hi, my name is Alexei, and I have a question from a bit of different angle. So I'm used to this SoC, like system on chip business world, and in which there are three roles in that business. One is a foundry, company who does chip production, and one is IP vendor who do a different kind of IPs. It may be memory IP, maybe it's processor IP, and maybe it's RAM and as IP. And there is a SoC integrator role where somebody who decides about the purpose of a chip takes those IPs and integrates them together and go to the foundry. Does it make sense to position these IPs that you have, which is multi-core kind of hub IP, as IP, and give it to like maybe hard IP, but give it to somebody who want to integrate it inside the SoC, how as vendors do, and then that's their job to integrate SRAM, flash, and all other interfaces, and it's will also be scalable thing, so you can configure it to how many cores you want and so on. And does it make sense from your perspective to go this route?
That has been offered on our website since, well, basically 2010. And exactly one potential customer has talked to us about possibly using our nodes to make smart pins on a chip that they were making. But otherwise, nobody's expressed an interest. If somebody writes us a check, they can have GDS for nodes for a reasonable business basis. Yes. It's just a question that needs to be asked.
Hi, Greg. Franklin here. I was wondering if you had plans to add routing around the nodes at some point so that node A, say at the corner of a chip, can talk to node B somewhere else on the chip without going through the nodes?
There is room in an F-18 for another COM port's worth of drivers and receivers. We haven't yet been bright enough to see a way to deploy that capability that would address more than one application. So, suggestions are welcome. Suggestions are always welcome, but it appears offhand that actually Dean Sanderson's idea of putting some I/O nodes in the center of the chip holds more water than worrying about what to do with warp ports and making some cockamamie geometry that serves one application and not any others. The central reason for getting stuff across the chip of great distances that is obvious is when pins on one side of the device have to talk to pins on the other side. And that's what Dean was thinking, was getting the I/O, getting some I/O closer together might ameliorate that.
Greg, this is Bob Nash, and I have, two questions. First of all is about your app note number 7, and I was looking there, you were talking about synchronizing to an external 10 megahertz source for timing, and you said that something about it being necessary because of the standards, but and it looked like there was an awful lot of or could be a lot of time chewed up just trying to synchronize to an external signal. Oh, okay, and I was wondering if you could talk about that a little bit. And then also, I'm just curious, how much SRAM do you think you would need, minimum, and how much do you think you might be able to get? Or I'm sure you must have looked at that. Just hand-waving sort of level there.
Okay, we back on? Okay, Bob, thank you. Okay, I see the answer from Sam. Great. With respect to the first one, if there's one thing we do exceptionally and unparalleledly well, it is synchronizing to external signals. The time delay between an external event happening and a node taking off that's waiting for that external event on a pin is the time it takes to charge up the capacitance of the pin, mostly. And that's the time that it takes to charge up 2.5 picofarads. So it depends on how hard you're prepared to drive the pin as to how long it takes us to notice something. But otherwise, noticing it is the propagation of a signal at most a couple of millimeters and then 1 gate delay. And that's not very significant. It's under 100 picoseconds. So no, I mean, if you take anybody else's computer that has a clock, then the amount of time uncertainty and jitter in synchronization with an external event is at minimum 1 clock cycle, right? And in our case, there is no clock, so there is no such jitter. So actually, we do an exceptionally good job, and that's one of the reasons why I kind of, with my tongue in cheek, giggle at the idea of somebody sitting down with a clocked computer trying to do the Manchester decoder that we do with the Ethernet, because he's already got a giant variable in there on the detection of the edge and when that edge actually happened in the first place, whereas we're dead nuts lock sync to it. The issue is I've actually watched other people's NICs drift if we gave them a slightly marginal frequency. And you know, you sit there and they're synced all through the 62-bit preamble, and then somewhere during one of the MAC addresses they lose it. You just look at the bits. They're right, and then all of a sudden they're wrong. You know, and that's obvious what happened. Now, when you have a jumbo packet, it's way worse than that. These errors are accumulative, so that's a problem. As far as the other question was concerned,
it was how much RAM?
Yes, thank you. The how much RAM? Well, we've all programmed 16-bit machines in Forth, and so naturally I'd like at least 64K bytes or 128K bytes, depending. But being able to fit 64K bytes worth of ARM SRAM onto a reasonable chip is probably about the maximum that we could hope for. But we'll know in a month or two at the most. All it's going to take is firing up the Spark and telling it what to do, and then starting to compile SRAM. We did that at 28, but it would have been a moot point. We can't afford to go 28 nanometers. Buying a set of masks and a run there is $3 million. We can't do that.
I just have one more kind of out there question. So you keep mentioning 28 nanometer process. I'm just curious, what would a F18 run at? How fast would it run? Much faster at 28 nanometers, theoretically, wouldn't it?
At most 10x. At most 10x. We're eating into Chuck's fireside chat time at this point, and I suspect that y'all would like to go to supper. Are there any more questions?
It looks like we have no more questions, Greg. Thank you very much.
Well, thanks a lot for putting up with us being this way this time, folks. I'm real sorry that I was out driving around in the snow instead of...
Okay. He's taking that out. I'm just going to hand this over to Chuck right now. Chuck. Oh, you hold it? Yeah. Oh, okay. No. Let's stick that somewhere. Yeah, there you go.
Find a place to stand, and I will find you.
There goes the fire.
Okay. Nice to see you all again. I look forward to doing this every year. And I'm already planning what I'm going to be doing next year. Let me expand a little bit about what has been said here today. First, you may notice the GA144 is very easy to program. There's very little code required to program a node. And that is a good thing, a very good thing, because you have 144 nodes to program. So if you only have 10 lines of code in a node, that's still 1,500 lines of code total. But it is easy. It factors the problem for you automatically into small pieces that the mind can grasp. And the interaction amongst all these pieces is automatic and leads to impressive results. Another thing, the GA144 already has 18,000 bytes of memory, of RAM, distributed among 144 computers. So each computer only has 64 words, but the total amount of words is substantial. About 1/3 of the chip is required to accommodate that much memory. So yes, we could have some tens of thousands of bytes of RAM at the cost of some of the nodes. Take out some nodes, replace them with RAM. Is that a good trade-off? I think it probably depends on the application. You can do an awful lot with the 18,000 bytes you've already got. So I wouldn't hold up waiting for more RAM. It's already there. Now, Greg spoke of this project we had a year ago, and it was fun. The most of what I did was I designed a 32-bit adder. I'm very pleased with the results of that experiment, because my adder is faster than any adder I know of, especially on the average. What I do is detect the carry propagate. And when the carry propagate is finished, the add is finished. This means most adds are one cycle, instantaneous, because the carry doesn't go very far. The worst case, the carry's got to go 32 bits or 31 bits. It takes a long time, 10 times longer than minimal. So this clever, not look-ahead adder, this, I call it a carry complete adder, is nice, is neat. And if I ever design a 32-bit version of the chip, an F32, I will include that adder and we'll have fast multiplies, or fast adds. The downside is the add time is variable. You can't count the number of cycles required to execute a piece of code because it depends on the data. But that is a small price to pay for a fast add, because a fast add leads to a fast multiply. All right. Some years ago, I talked about the map is not the territory. And there's an ancillary concept that this is not a pipe. You may recall that famous painting. The discrepancy between your description of something and something itself is large and in many cases imponderable. An example of that is cosmology. Cosmologists are building a model of the universe, and that model tends to dominate our thinking about what the universe is. And that model is not the universe. It isn't even perhaps very close to what the universe actually is. We just don't know. Cosmology, the ultra-large, and quantum mechanics, the ultra-small, have very loose connections with reality, whatever reality is. I want to give you a little history about Forth. This is the 46th anniversary of the first Forth, if you can count, plus or minus one maybe. I am developing a new Forth, which I want to talk about today. I call it 46.0 because every Forth with a little letter in front of it has already been taken. Forth 1.0 was an interpreter in the most brutal sense of the word. It was coded in Fortran. It interpreted text. In other words, at runtime, the interpreter read a string of characters, parsed them into words, looked up the words in a dictionary and executed the word, and went back and looked up the next word. It was brutally slow, but it was fast enough, and it was fast compared to some of the alternatives. Forth, maybe 3.0, had indirect threaded code, which was enormously faster. Because it was faster, it was much more useful, and it was much more efficient. But indirect threaded code, as we've seen today from Ting, is not all that swift. Somewhere along the line, I went to subroutine threaded code, and I don't remember when that was. Forth X.0, probably 10 years later. Indirect threaded code satisfied requirements for a long time. The big change came at 32.0, which was color Forth. Color Forth is a strange beast. It is incredibly unpopular, even amongst people who should know better. It introduced three things. First, it pre-parsed the source code, which cut compile time in half. What a compiler does is the classic compiler would take a string of characters, parse them into words, and look up the words in the dictionary. If the words are pre-parsed, you don't have to parse them, and you save about 50% of your compile time. Colorforth also introduced Shannon encoded characters, which was a neat trick of no great value. And it required you use a special editor, which people are loath to do. People like to use their favorite editor. And finally, it introduced a weird keyboard that nobody was willing to learn to use except me. And I never did learn to use it very well. I had to have enough background lighting that I could see the keys and know where my fingers were and what I was doing. But Colorforth changed the balance. The classic cycle of debugging a program is to edit your source code, compile your source code, and run your object code. This edit, compile, run is sort of the mantra of Forth interactive testing. By cutting the compile time in half, Colorforth moved the burden from the compiler to the editor. The compiler is used much more often than the editor, so that's a good trade-off in efficiency of computer execution. Well, let's go back to 144. Greg outlined what he has in mind using Polyforth to run on the 144 and make it sort of a standalone, independent of the host computer, although you still need a host computer to act as a terminal, or something to act as a terminal. I heartily agree with this, that the 144 should be a standalone computer. But I have a much more ambitious way of doing it, and that is Polyforth is not relevant. Polyforth is old school. I want the 144 to be a standalone. So for the last couple of years, I've been working on, not 100% of the time, but cogitating on how I could make a 144 group of nodes compile its own code. And I got really close to that. It took about 6 nodes. But it required a couple extra nodes to actually store the source code on chip and generate the object code, have a place to put the object code. And I was kind of discouraged because it was all getting too complicated and difficult, so I was not looking for a better way, but a better way occurred to me. And that's what I've been doing for the last, couple of months, very aggressively. And it's coming along in a very interesting way. I don't know if anyone's done this before, but I certainly haven't heard of it. And that is eliminate the compiler. Eliminate the source code. And have a very nice decompiler, which will let you look at the object code. This works particularly well on the 144 because you have 64 words of code in each of the nodes. So you can look at these 64 words of code, decompile them into something that looks just like Colorforth, and never have to compile it. Instead, what you have is an editor that can edit the object code. And that's not hard to do. It has its own complications. But it is in my mind, it looks like a very promising way to simplify the whole project of generating code in these small chunks for these small computers. Now, that doesn't necessarily have to work only on the 144. I've developed 2 versions so far. One running on the PC, and one running on a Mac. And it does really seem to work. That you can look at object code, whatever that means. It needn't be in machine instructions. It could be some interpreted high-level instructions. And edit them. Now, editing object code has one substantial feature. First, if you insert an instruction in an instruction stream, everything downstream of it shifts, and you have to update all your addresses everywhere. But that is not insuperable. That merely takes computer time. And the computer has all the time in the world at edit time to do such things. So once you have this chunk of object code, self-contained, maybe making references into the system code somewhere, which is their absolute addresses, you can download it instantly, you can document it carefully, and you never have to compile it. But you need one more thing. I tried to do this 5 years ago, or 10 years ago, 15 years ago, and failed abjectly because I couldn't figure out what the decompiler was trying to tell me. It was not documented. So what you need in addition to this object code is a wrapper, which contains basically the dictionary. Pointers into the object code telling you names of things, comments associated with things, helpful comments, expressions, whatever. Maybe some control information of where this goes and what starts it and what stops it, which is all easy to do. It requires another element, this dictionary, and tools that let you edit the dictionary, build the dictionary, but that's cheap compared to a compiler. So I'm absolutely intrigued by the possibilities of this. To design the wrapper is a challenge. I've done it 2 or 3 times so far, and I haven't gotten anything that's satisfactory. But that's a solvable problem. The object code is no problem at all. That's just, you've got object code anyway. It's just a question of where it came from. And that, I think, will lead to a 144 being able to program itself, or that with a handful of nodes, no need to manipulate source code. The way the 144 works, the way my 144s work, is that the decompiler would look at the object code, which is stored in a node. It's one node's worth of code. Interpret words, instructions one at a time, generate output, the source that goes along with them, and send that source out to a display. The display is being continually updated, so the decompiler has to work at 60 hertz. But that is possible to do. I've demonstrated that. So you don't need any source code. You don't need any memory to store the source code. You just need the object code, and you interpret that. There are some interesting twists, which I won't get into here. What I plan to do next year is show you that it's running, and have some very interesting applications. It is easy to program a node to do impressive things. No, you can't. I'll take that back. It's easy to program a bunch of nodes to do impressive things, each node of which is quite simple. And I think this decompiler application will be an excellent example of that. All you need is an input device to program a 144. Now, I'm eternally optimistic. I'm thinking that if a 144 is easy to program, more people will program it, and we'll start selling some chips. On the other hand, it never works out that way. Whatever the resistance is out there isn't going to go away just by waving your hands at it. But hey, what can I do but try? And the fact that this does simplify things, I'd like to say enormously, but I'm not sure how complicated the decompiler is going to end up being. So maybe it isn't enormously, but significantly. By the by, we've seen some examples of decompiling today. Decompiling is not a new concept. In fact, I don't know, maybe someone else has already done what I'm talking about. But the wrapper is the key. The fact that you can document your decompiled code and get something that looks as good as sourced forth. If anyone can think of a good abbreviation for sourceless forth, let me know. What else? Let me check my notes.
What you see is what it is.
Sorry?
Oh, what you see is what it is.
Yes, exactly. Now this isn't going to work for C. You can't decompile such an application in any intelligible way. But Forth has a very simple instruction set. In fact, as soon as you eliminate the compiler, the instruction set gets even smaller. You don't need if and then and do and loop, because those are just jump instructions, which you decompile into something that resembles what they were. Potentially, it releases some of the constraints on structure, that you could have nested if-thens that jump outside of their natural range. I can't think why you might want to do that, but it would work. It eliminates the need for vocabularies. Even if you have a pretty large application, the name that you give a word or an entry location need not be unique. It's merely a comment. It's merely a helpful aid to your recognition of what the intent of the code is. So you can reuse words without any confusion because they're just labels. It eliminates the meta compiler. You don't have any confusion about the code you're executing and the code that you're generating for the same reason. The names are not relevant. The names are merely comments. So the classic edit, compile, run cycle becomes edit, run. And edit has two pieces. It has decompile and edit object code. I don't even have the words for these things yet. But basically, edit, run is a lot more attractive than edit, compile, run. Any of you, you're welcome to try this on your own if you like. I've got no claim to uniqueness.
Say swap the letters, it becomes report. Report, run edit, report,
Okay, all right. If no one's used that. I was going to use some nice, clever first letters, but then I decided I better Google them, and I did, and then, is there anything left? Is there any letter no one's used? Fourther? Fourth 46.0 is pretty clumsy. In fact, it probably isn't even going to, it doesn't have a prayer. It'll be fourth 47.0 before very much longer. I can actually guesstimate that I've probably programmed 46 fourths in the last 46 years. Not one every year, but some years were productive and probably made up for the ones that weren't. And that is either impressive or depressing, depending on how you think of it. Has it been worth doing the same thing 46 times? That's a sign of insanity. Excuse me. There are a whole spectrum of fourths. I break them into megafourths and, I don't know, microfourths. Certainly the fourth that is relevant for the 144 is a microfourth. It doesn't need very much syntax. It doesn't have very much flexibility, but it's adequate to the task. And I think my fourth needs to be scaled down so that it is not overkill for that very simple problem. Greg takes a different approach. I don't know if you're familiar with polyforth, but it's what I think of as a megaforth. It has lots of power, lots of capabilities, multi-programming, all kinds of power that you don't need for a simple thing like programming a 144.